Chapter 3: Biological Food Safety Hazards for Human Food. Presented by David Rosson. In developing or modifying a food safety plan, it is important to be aware of the potential hazards that are associated with the food products and processes under consideration. When hazards are understood, preventive measures can be implemented to control those hazards, thus preventing illness or injury. This chapter introduces the definition of the term hazard, discusses biological hazards that are commonly of concern in food processing plants and facilities holding food products, and reviews potential controls for biological hazards. By the end of this chapter, participants will be able to define the term hazard, recognize the significant impact of biological hazards, recognize potential biological hazards, their sources and contributing factors, identify potential controls for these hazards. The Preventive Controls for Human Food Regulation defines hazard as any biological, chemical, including radiological or physical agent that has the potential to cause illness or injury. Biological hazards include pathogenic bacteria, viruses, and parasites. Chapter 4: Chemical, Physical, and Economically Motivated Hazards covers chemical, including radiological and physical hazards, mentioned in the definition. Information from this chapter on biological hazards and Chapter 4 on chemical, physical, and economically motivated hazards is useful for conducting a hazard analysis for a food to determine which hazards will require a preventive control. The hazard analysis process is discussed in Chapter 6, Hazard Analysis, and Chapter 7, Preventive Controls Determination. It is important to understand that for the purposes of food safety, the term hazard refers only to the conditions or contaminants in food that have the potential to cause illness or injury to people. Many conditions are highly undesirable in food, such as the presence of insects, hair, filth, or spoilage. Economic fraud and violations of regulatory food standards are also undesirable. All of these defect conditions should be controlled in food processing. However, many times they are not directly related to the safety of the product. Unless these conditions directly affect food safety, they are not included in a food safety plan. The Preventive Controls for Human Food Regulation does consider decomposition to be a potential food safety hazard when biogenic amines or other toxic substances are produced that may cause illness or injury. How a hazard is addressed in a food safety plan depends on both the likelihood of its occurrence in the absence of its control and in the severity of the illness or injury that would result if the food were consumed. The difference between a known or reasonably foreseeable hazard and a hazard requiring a preventive control is explained in Chapter 6, Hazard Analysis for Human Food. The current chapter provides a general discussion of potential biological hazards in food products. The terms filth, foreign material, or extraneous material can be used interchangeably. The terms refer to any type of matter that does not obviously belong in a food product. Adapted from FDA's ORA Lab Manual, Section 4. To gain an understanding of the issues related to hazards encountered in the food supply chain in terms of size and scope, two governmental reporting systems are commonly used. The United States Centers for Disease Control and Prevention, CDC, reports outbreak data that provides information on those hazards responsible for foodborne illness cases. CDC defines a foodborne disease outbreak as an incident in which two or more persons experience a similar illness after ingestion of a common food, and epidemiologic analysis implicates the food as the source of the illness. The other source for understanding the issues of hazards specific to product types encountered in food supply chain is FDA's Reportable Food Registry. The Reportable Food Registry, RFR, or the registry, is an electronic portal for industry to report when there is a reasonable probability that an article of food will cause serious adverse health consequences in humans or animals. Foods listed in the Reportable Food Registry are examples of food products and hazards that can cause serious adverse health consequences or death to humans or animals. The registry helps the FDA better protect public health by enabling the tracking of patterns and targeting inspectional resources. Published in 2011, the CDC's estimates of the burden of foodborne illness in the United States provide the most accurate picture of known pathogens and unspecified agents causing foodborne illness in the United States. These estimates serve as a foundation for food safety by answering the important question of how many foodborne illnesses occur every year. These estimates are known as the burden of foodborne illness. Note that the data may be updated in the future as CDC reassesses estimates. The Centers for Disease Control and Prevention, CDC, surveillance data on foodborne disease outbreaks, i.e., 2 or more persons experience a similar illness after ingestion of a common food, are illustrated above. The number of illnesses reported is just the tip of the iceberg, because many foodborne illnesses are not reported to CDC. However, the data is useful in understanding the types of hazards that are likely to cause illness. Biological hazards, including pathogenic bacteria, viruses, and parasites, are the most frequently reported hazard group associated with foodborne illness in the United States. Chemical agents are also reported, but as shown on the slide, reported numbers are much lower than those for biological hazards. Food allergen reactions may not be captured in the CDC data because an outbreak requires two or more people from separate households to be ill from the common food, but allergenic reactions are sporadic and likely involving only one person at a time. CDC surveillance systems do not report physical hazard outbreaks. CDC surveillance data include confirmed and suspected foodborne illnesses that are reported by states. These numbers are just the tip of the iceberg and do not include adjustment factors for underreporting. Check out the CDC beam. Dashboard, originally known as the food tool, to do some of your own research. The impact on human health from food contamination varies with the type of agent. While viruses and bacteria are the most common foodborne pathogens, outbreaks associated with viruses, such as norovirus, tend to be large, often due to the nature of how the virus spreads. However, the resulting illness is less likely to result in hospitalizations or death. Outbreaks associated with bacterial pathogens tend to be more serious in terms of human health impact. Parasitic infections seldom occur, but when they do, their impact is serious. Estimates of foodborne illness can be used to prioritize food safety policy and interventions. Scallon et al. Used data from active and passive surveillance and other sources to estimate that each year, 31 major pathogens acquired in the United States cause 9.4 million episodes of foodborne illness, 55,961 hospitalizations, and 1,351 deaths. The goal of the hazard analysis, to be discussed further in Chapter 6, is to identify what biological hazards can be introduced into a food product from ingredients and other raw materials, from food processing equipment in the facility environment used to make the final product, and from people handling the product during harvesting or processing. Once identified, the food safety team will evaluate those hazards and determine which hazards will require a preventive control. Pathogenic bacteria, parasites, and viruses are different kinds of biological hazards. Control strategies are discussed later. As discussed earlier, a useful source of information on the hazards that may be present in different foods is FDA's Reportable Food Registry. See additional reading at the end of the chapter. This registry collects information from the food industry and from public health authorities on foods and feed that are likely to cause serious adverse health consequences or death to humans or animals if they are used. As shown in the pie chart on the slides, biological hazards represent the primary category of hazards reported through the registry for human food. However, undeclared allergens in human food represent more than 1/3 of the reports. These are discussed in Chapter 4, Chemical, Physical, and Economically Motivated Hazards. Microorganisms are living life forms that are too small to see with the human eye. Microorganisms are present in air, dirt, water, skin, hair, plants, and numerous other sources like saliva and air expelled with coughs and sneezes. Microorganisms are classified into various groups, including bacteria, viruses, protozoa, and molds. Many microorganisms are beneficial. Certain kinds of molds and or bacteria help make cheese, sour cream, yogurt, sausage, pickles, sauerkraut, and other fermented products. These microorganisms are intentionally added to foods, and they cause no harm. People come into contact with thousands of kinds of molds and bacteria, viruses, and protozoa daily with no ill effect. In fact, bacteria live naturally on our skin, in human noses, mouths, and in the digestive tract. They play an important role in digesting food and are part of a healthy human system. The focus is on those specific microorganisms considered biological hazards in food because they can cause illness and injury. There are more than 30 different known foodborne pathogens. This includes types among the groups of bacteria, viruses, and parasites. Some molds produce hazardous toxins called mycotoxins, which are considered chemical hazards in this course. See Chapter 4, Chemical, Physical, and Economically Motivated Food Safety Hazards. Prions are typically considered a biological hazard and are proteins that can cause mad cow disease, or in technical terms, bovine spongiform encephalopathy or BSE, and similar diseases in other animals, including certain types of game. Prions are not covered in this course, but see the FDA's Bad Bug book listed in additional reading for more information applicable to a facility processing game animals under FDA authority. Let's look at an important definition. Pathogen, a microorganism of public health significance. 21 CFR 1:17.3. In this course, the term is generally used to refer to microorganisms that cause illness through the consumption of food. The reality is that foods can become contaminated anywhere along the food supply chain, so controls may be needed at multiple points. Sources of biological hazards include supplier level, ingredients that may be contaminated from the field during growing and harvesting, or at the supplier's processing facility. During transportation, pest contamination during transport can introduce microorganisms. During processing, cross-contamination of equipment and or the environment if they are not cleaned and sanitized properly. From personnel, people handling food. Foodborne illness can occur when there is the lack of control at these points. As mentioned, lack of control at specific points in the food supply chain can result in contaminated food. Two important categories of food that will have specific controls are 1. Those foods that support the growth or survival of pathogenic organisms, and 2. Those foods that are considered ready to eat. Foods that support the growth or survival of pathogenic microorganisms will need controls, such as time and temperature control, to limit pathogen growth, if present in the product. In the latter, ready-to-eat foods will be consumed without any further preparation by the consumer, so any pathogens present on the product will be consumed along with the product. Foodborne pathogens may cause illness in humans by either infection or intoxication after the food is eaten. Foodborne infections are caused after consuming live pathogens from contaminated food, which then grow in the human body, usually in the intestinal tract, and cause illness. Because growth in the body is required for an infection, considerable time can pass before symptoms occur, typically between 24 to 72 hours, but sometimes even longer, e.g. weeks. Viruses, parasites, and many bacteria in food can cause foodborne infections. It is important to note that growth in food may not be necessary to cause illness. For example, some infectious bacteria, such as E. coli O 157:H7, can present a potential hazard simply due to its presence in the food when consumed, whereas other bacterial pathogens require growth to a level that can make people ill. The specific symptoms depend on the pathogen and the susceptibility of the person eating the food, and can include nausea, vomiting, diarrhea, and sometimes fever. Illness can sometimes lead to hospitalization and even death. Foodborne intoxication is caused by consuming foods with preformed toxins produced by high numbers of certain bacteria, e.g. Staphylococcus aureus, Clostridium botulinum, and certain strains Bacillus cereus. Symptoms from foodborne intoxication usually occur more rapidly than those from a foodborne infection, and illness can occur as soon as a few hours after consumption. Restricting growth of toxin-forming pathogens in food will prevent the risk of foodborne intoxication. If toxins are in food, reheating the food will not necessarily inactivate the toxin and make the food safe. See Appendix 4, Foodborne Pathogen. Supplementary information for information on different foodborne pathogens, including symptoms and parameters that can control growth. The table on the slide lists examples of common biological hazards and in what foods they are found most frequently. Note, this table of common sources of biological hazards is not an exhaustive list and provides only broad discussion groups. The biological hazards are bacterial pathogens, e.g. Salmonella spp, Listeria monocytogenes, Clostridium botulinum, and Shiga toxin-producing Escherichia coli, STEC, such as O157:H7, that may be associated with foods that can cause consumer illness or disease. Chronobacter species, including C. sakazaki, has emerged more recently as a hazard largely for powdered infant formula, rather than a hazard applicable to foods for the general population. It can survive in dry environments. Note that infant formula is covered under the preventive controls for human food regulation, in addition to 21 CFR Part 106 and Part 107. The other biological hazards, viruses, e.g. norovirus and hepatitis A, and parasites, e.g. Cryptosporidium apiciis and Giardia intestinalis, are also known to cause illness or disease, but these would generally be addressed by following worker hygiene and disease controls. Provisions of GMPs in 21 CFR Part 117 and 21 CFR Part 112, standards for the growing, harvesting, packing, and holding of produce for human consumption, on farms that supply raw agricultural commodities to processing facilities. Chapter 6. Hazard analysis will cover more details about resources that can be used to identify potential ingredient-related biological hazards, e.g., FDA Hazard Guide. There are many potential sources of biological hazards from the process itself, referred to as process-related hazards. These types of hazards could include survival of pathogens, if the process is not adequate to inactivate them, improper cooling that could allow outgrowth of spores or contamination from ingredients added after the process control. Other potential sources of biological hazards could include the facility itself, referred to as facility-related hazards. Listeria monocytogenes is typically more of a concern in wet processing environments, and Salmonella and Chronobacter in dry environments. People, food handlers, can also be a source of hazards from shedding in their vomit or feces, Shigella, Salmonella, Hepatitis A, norovirus, or parasites, or from skin lesions or wounds, Staphylococcus aureus. Food handling hygienic practices are essential when handling products post-process. Chapter 6. Hazard analysis will cover more details about resources that can be used to identify potential process, facility, and people-related biological hazards, e.g., FDA Hazard Guide. 3 basic strategies can be used to control bacterial pathogens in food. 1. Prevent contamination. 2. Reduce or eliminate the bacterial pathogens. And 3. Control the growth of the bacterial pathogens. The primary prevent contamination approaches include personal hygiene practices, GMP-based sanitation, and appropriate handling of ingredients and direct contact packaging. Keeping pathogens out of food can be accomplished through the practice of good personal hygiene by food workers. These practices would include wearing outer garments suitable to the operation to protect against cross-contamination of food, food contact surfaces, or direct food packaging materials, maintaining adequate personal cleanliness, washing hands thoroughly to protect against contamination with undesirable microorganisms, and maintaining gloves if they are used in food handling in an intact, clean, and sanitary condition. Preventing cross-contamination of food can also be accomplished through effective sanitation practices. These practices would include the cleaning and sanitizing of utensils, equipment, and the facility environment to protect against cross-contamination of food, food contact surfaces, or direct food packaging materials. Appropriate handling of ingredients and other raw materials in food contact packaging is essential to minimize the introduction of pathogens into the facility and the food. Certain ingredients and other raw materials can be the source of pathogens, and if those items are not properly processed, contamination will be present in the finished product. Another concern is that those items can be the source for cross-contamination in the processing environment, so controls must be in place to prevent cross-contamination. Inactivation and elimination are terms that refer to reducing pathogens to a level which is no longer a public health concern. Thermal treatments, such as cooking, pasteurization, retorting processes are frequently used to destroy pathogens. Other processing techniques, such as irradiation, high-pressure treatments, antimicrobial chemicals, e.g., sanitizers, acidification, ultrasound, and pulsed light, may also be applied to food or to food contact surfaces to destroy pathogens. All food processing techniques must be validated to the specific food and processing conditions to ensure effective and consistent control of the pathogens of concern in the specific food. Process validation is important to establish the necessary parameters, taking into consideration the factors that may influence the rate of pathogen inactivation or elimination. These factors may include the specified time and temperature, food composition, or formulation, e.g., pH, moisture content. For example, for cooking to be successful, the food must reach an adequate temperature for a long enough time to kill the microorganisms of concern. Higher temperatures kill faster than lower temperatures. The required temperature depends on the food, the pathogen of concern, and the time involved. Adequate cooking temperatures may be established for certain pathogens and/or foods. Ethylene oxide, EDO, or propylene oxide, PPO, are used to reduce microbial contamination, such as by the spice industry, against E. coli and Salmonella. Appendix 4, Foodborne Pathogen. Supplementary information provides time and temperature guidance for controlling pathogen growth and toxin formation, as well as inactivation of Listeria monocytogenes. FDA Food Code provides safe cooking time and temperature combinations for a variety of foods. See additional reading. FDA Dairy Hazard Guide also provides safe cooking temperatures for certain products. See additional reading. Other validated time and temperature combinations may also be appropriate for certain foods. Bacterial hazards can be classified as bacterial pathogens, which exist only in the vegetative state, non-spore formers, and those that can form spores, spore formers. Both need to be considered. Bacterial spore formers are notable for their ability to produce spores, which can survive harsh conditions that destroy other pathogens. Spores are similar to a seed in that they have a hard, resistant structure that allows survival through harsh conditions. In the photo above, the bright ovals are heat-resistant Bacillus cereus spores, and the larger dark rod-shaped bacteria are Bacillus cereus in its vegetative state. Spores are not hazardous as long as they remain in the spore state. Spores are very resistant to heat, chemicals, and other treatments that would normally kill vegetative forms of both spore formers and non-spore formers. When spores survive a processing step designed to kill vegetative bacteria, they may become a hazard in the food if they are exposed to favorable conditions that allow germination and growth and subsequent toxin production. This can be particularly serious when a processing step has removed most of the existing competitive microflora, leaving the spores to grow unabatedly. Provided conditions are right, the processing steps used to kill spores are often much more severe than those necessary to kill vegetative cells, because spores are more resistant. It is very important to consider the potential for growth of spores and control them appropriately. It is important to note that in some cases, destroying one type of hazard can provide an opportunity for other hazards to emerge because competition is eliminated. Some types of microorganisms are more resistant than others to inactivation methods. Thus, it is important to understand the potential of pathogens of concern in a specific food and of spore formers and have the proper controls. Validation is the demonstration that the controls applied actually control these hazards, discussed in Chapter 10, Process Preventive Controls for Human Food, Verification and Record Keeping. A couple important definitions: spore, a dormant, resistant form of certain bacteria; vegetative cell, the growing form of bacteria. Bacteria have certain requirements to live and grow in food, including a nutrient source, time and temperature, a suitable pH, water available in the food, the proper atmosphere, and other factors. Microbial competition and the presence of preservatives may also affect the growth of bacterial pathogens. If conditions are not favorable for growth, some bacteria die while others persist until their growth requirements are met. Controlling a combination of these factors with the purpose of restricting pathogen growth is called the hurdle approach. More information about this is found in the upcoming slides. It is worth noting that growth inhibition does not necessarily mean that the pathogen is killed. Many pathogens can survive in conditions that prevent growth and may cause disease. Keeping microorganisms from growing can be an important control when the process does not kill potential pathogens, e.g., spores, or when products may become recontaminated after a lethal process, e.g., ready-to-eat products that are exposed to the environment after cooking before packaging. Preventing growth also may reduce the risk of foodborne disease because some pathogens must grow to a sufficiently high number to present a hazardous situation, such as when toxin production or a high infectious dose is needed to cause illness. Time and temperature, the level of acidity, pH, available water, water activity, or a W, the right level of oxygen, atmosphere, the presence of competition by other bacteria, and preservative use can all influence growth of potentially harmful bacteria. It can sometimes take bacteria a bit of time to start growing, lag phase, but then under favorable conditions it takes off and grows rapidly with one bacterium, dividing into 2, 2 into 4, 4 into 8, 8 into 16, and so on. Growth phase. Under ideal conditions, some bacteria double every 20 minutes. Thus, one bacterium can multiply to more than 30,000 in 5 hours and over 16 million in 8 hours. If relevant, toxin formation usually occurs during exponential growth. Growth continues until it runs out of what it needs to keep multiplying, stationary phase, and then it can start dying off, death phase. Even after death of the organism, any toxin it produced will remain active and could lead to a food intoxication. Ideally, growth will be prevented due to the nature of the food itself or through application of preventive controls. It's a good time to introduce the logarithmic scale. A logarithmic log scale is used to plot microbial growth because of the rapid increase in numbers. Simply put, there is a tenfold difference between each unit on a log. For example, a log unit of 2 is 10 times more than a log unit of 1. Similarly, a log unit of 5 is 10 times more than a log unit of 4. For example, log 3 equals 1,000. Log 4 equals 10,000. Log 5 equals 100,000, etc. Cold temperatures typically control bacterial growth. However, some pathogens can grow at refrigeration temperatures, such as Listeria monocytogenes. As temperatures rise, growth rates increase. Improper holding temperatures for food may allow foodborne bacteria to multiply, as discussed in the previous slide. Very rapid growth of foodborne pathogens can occur between 77 degrees to 104 degrees Fahrenheit, 25 degrees to 40 degrees Celsius. The range of temperature that supports pathogen growth varies considerably, depending on the specific organism, see Appendix 4, and other characteristics of the food. Guidelines have been developed for how long food can be held at potential growth temperatures. For example, cooling models have been developed for Clostridium perfringens. Because of the potential for its rapid growth and toxin formation, if there is prolonged or inadequate cooling of soups and sauces, the direct temperature of the food is the primary control of the organism, not the temperature of the environment in which the food is held. For example, even if a refrigerator or cooler is at the proper temperature, food placed in it may not cool down rapidly if the container is large or constructed with insulating layers. See Table A 4-2 in Appendix 4. Foodborne pathogen supplementary information for guidelines on the maximum cumulative time and food temperature combinations for controlling growth and toxin formations for foodborne pathogenic bacteria. In general, holding food at temperatures between the proper refrigeration temperature for the product and 135 degrees Fahrenheit, 57 degrees Celsius, should be avoided. This is the danger zone within which bacterial pathogens can grow. Pathogens typically grow at temperatures up to 135 degrees Fahrenheit, 57 degrees Celsius. So, holding hot foods above this temperature limits growth of microorganisms. As stated earlier, spore-forming bacteria, such as Bacillus cereus, can be activated with a cooking step, but chilling of cooked foods can restrict its growth and possible toxin production. The pH of a food is a measure of its acidity or alkalinity. Foods with a pH less than 7.0 are acidic. The pH of a food can be measured using a pH meter or pH paper. A pH below 4.6 prevents the growth of many bacterial pathogens, such as Clostridium botulinum, which is a deadly pathogen. However, some pathogens can grow or survive below 4.6 pH, depending on the food, temperature, and other factors. See Appendix 4, Foodborne Pathogen Supplementary Information. For example, Salmonella, the most common bacterial hazard associated with foodborne illness, has been reported to have a minimum growth pH of as low as 3.7. While a low pH may prevent bacterial growth, some pathogens can survive. Do not assume that a low pH will necessarily kill a pathogen. Notice that some foods, e.g. lemons and vinegar, have very low pH values, where pathogen growth will not occur. Others, e.g. milk and eggs, have pH values, where growth is likely if other conditions, such as temperature, are favorable. Clostridium botulinum growth is inhibited by a pH less than 4.6, but other pathogens may grow or survive below this pH value. See Appendix 4 for more information. If the safety of a product depends on pH, the facility must use a reliable pH test method. FDA methods for measuring pH of acidified foods are found in 21 CFR 114.90. Methodology. It's important to note, sometimes the addition of other ingredients can change the pH or water activity of a food. Pay attention to this if these factors are used to control growth. All forms of life require water to grow, but it must be available, that is, not bound up with other molecules, to allow for growth. Water activity, AW, is a term used to describe the availability of water, free moisture, in a food. Pure water has a water activity of 1.0. Adding solids such as salt, sugar, and similar food ingredients can reduce the availability of water for microbial growth. Think about seawater. Some species thrive in the ocean rather than in a freshwater lake. The same is true for microorganisms. Growth of pathogenic bacteria is restricted when the water activity is equal to or less than 0.85. Staphylococcus aureus is the only foodborne pathogen that grows below 0.94 water activity, the level below which most pathogens are inhibited from growing. But the pathogenic bacteria will continue to survive, and the heat inactivation requirements may be increased under conditions of lowered AW, especially for pathogens like Salmonella. This means higher levels of heat or longer heating times may be required in low foods for pathogen inactivation. Many fresh foods have water activity values above 0.96, which supports the growth of pathogens. There are also many dry foods with water activity values below 0.6, which inhibits pathogen growth, although some bacteria, such as Salmonella, can survive for long periods of time. In between, there is a range of foods that may have water activity values that support growth of some pathogens. Growth of pathogenic bacteria stops when the water activity is less than 0.85. Staphylococcus aureus is the only foodborne pathogen that grows below 0.94 water activity, and it can produce toxin down to a water activity of 0.86. Details on water. Activity limits for specific pathogens are provided in Appendix 4, Foodborne Pathogen Supplementary Information. It is important to recognize that the range of water activity values for some food categories can be quite broad. Specific measurements are needed for these types of products if water activity is used as a growth control strategy. For foods that have different components, such as a donut with a cream filling, the pH and water activity may be quite different in the components. In the donut example, the filling may be acidic and have a high water activity, while the donut part may have a near neutral pH and a lower water activity. The interface between the filling and the donut may be just right for microbial growth, which may be an issue if contamination of the interface is reasonably likely to occur. The report, Evaluation and Definition of Potentially Hazardous Foods, provides information on pH and water activity, combinations that prevent foodborne pathogen growth. See additional reading. Also see Chapter 10, Process Preventive Controls for Human Food, Verification and Record Keeping. Other factors that may influence the growth of microorganisms include atmosphere, microbial competition, and preservatives. Some pathogens prefer to grow at the concentrations of oxygen present in the air we breathe. Others prefer or even require little or no oxygen before they can grow. Of particular concern for food safety are anaerobic conditions, very low or no oxygen, that favor the pathogen Clostridium botulinum. Changing the packaging to control oxygen levels may change the hazards of concern for a food. For example, creation of anaerobic conditions through packaging can inhibit spoilage organisms and extend shelf life. The reduced oxygen packaging, ROP, process creates an anaerobic environment, which favors the growth of two pathogens, Clostridium botulinum and Listeria monocytogenes. ROP is often used to extend shelf life, which can provide more time for toxin production or pathogen growth if pathogens are present and temperatures are suitable for growth. Pathogens can also be introduced into a treated product after packaging if there is a lack of container integrity. This anaerobic environment and longer shelf life may provide an opportunity for unanticipated hazards, such as growth of Clostridium botulinum. Such changes should be carefully considered, and studies to validate product safety may be necessary. When there is little competition for nutrients, bacteria can reproduce rapidly. Conversely, the presence of other bacteria can inhibit the growth of certain pathogens. For example, production of toxin by Staphylococcus aureus may be suppressed when competitive bacteria are present. Fermented products like yogurt, which have high levels of active cultures, inhibit the growth of pathogens when fermentation proceeds at the normal rate. Preservatives like nitrite, sorbate, benzoate, and propionate, when formulated into food products, may slow or prevent the growth of pathogens, as well as spoilage microorganisms. The effectiveness of these preservatives depends on many factors. Thus, when relying on preservatives to control pathogen growth, validation is essential to ensure efficacy. C. Chapter 10. Process Preventive Controls for Human Food, Verification and Record Keeping. If not used at approved concentrations, some preservatives may be chemical hazards. See Chapter 4. Chemical, physical, and economically motivated food safety hazards for human food for more information. For many foods, bacterial growth often is controlled using one or more of the factors described above to make the food unsuitable for pathogen growth. Some preservation methods remove water, making this essential component unavailable to bacteria. For example, baking bread or crackers removes water from the food. Acidification is also a common method of preservation. For example, pickles, as is refrigeration, which slows growth, or freezing, which prevents pathogen growth entirely. It's important to note combinations of the factors that inhibit microbial growth can increase effectiveness and, in some cases, may even provide a level of inactivation. Data are needed to demonstrate that this occurs. The combinations of factors, such as pH and water activity, may inhibit organisms at levels where the individual factor alone would not. Some people refer to this as the hurdle approach. Using a combination of factors frequently requires expert knowledge to develop a stable combination. In the example on the slide, the organism is able to overcome a pH of 5.6 and grow. Even when the pH is lowered to 4.6, growth still occurs. It is only through adding new hurdles, such as decreasing water activity to 0.88 or adding a preservative, such as phosphate, that growth is halted. Combining such factors can help in limiting growth of harmful organisms in foods. Certain hard cheese products, including pecorino or Asiago cheeses, use a combination of lower pH and water activity values, along with bactericins produced by lactic acid bacteria that prevent pathogen growth. These are the primary bacterial pathogens, which commonly can be found in certain foods and cause illness that could be considered as biological hazards. Be sure to check out Appendix 4, Foodborne Pathogen, Supplementary Information for Similar Information for other bacterial pathogens. Understanding the characteristics of the pathogens of concern for the foods that a facility produces is important to select appropriate preventive controls. Salmonella is among the most common causes of bacterial foodborne illness. The infection causes diarrhea, fever, abdominal cramps, and vomiting. Occasionally, Salmonella may cause bloodstream infections and death. Severe cases may also result in reactive arthritis. Foodborne illness symptoms generally appear 12 to 72 hours after eating contaminated food. The intestinal tract of animals is the primary source of Salmonella. Thus, raw animal products, meat, poultry, eggs, and milk products are frequently associated with outbreaks. Many foods have been associated with outbreaks, such as unpasteurized, raw, milk, shell eggs, spices, tree nuts, yeast, coconut, sauces, cake mixes, cream-filled desserts, gelatin, peanut products, chocolate and cocoa, and soy ingredients. The initial source of contamination is the intestinal tract of animals. In addition to animals and eggs being the source of Salmonella, Salmonella is spread in the natural environment, where it can contaminate raw materials such as grain crops, produce, nuts, and spices. Good agricultural practices, GAPs, and compliance with the produce safety regulation in 21 CFR Part 112 play a key role in minimizing this contamination, but processing controls are normally employed as well. The food processing environment can become the source of contamination when salmonella establishes itself through contamination resulting from poor procedures involving raw material handling, facility maintenance, pest control, etc. Once in the facility, salmonella is an environmental biological hazard capable of cross-contaminating exposed post-processed product prior to packaging. Salmonella grows with or without air, grows best at human body temperature, grows very poorly at refrigeration temperatures, does not grow above 115 degrees Fahrenheit, 46 degrees Celsius, and some strains of Salmonella can grow to a pH as low as 3.7. Salmonella is easily killed at traditional cooking temperatures in high moisture products, but is shown to have significant heat resistance in dry foods, such as nuts and flour. Along with this, it has been shown to survive for extended times in dried state, whether that is in a dry product such as peanut butter or in a dry processing facility. It is best to keep dry environments dry when salmonella is a potential concern, since moisture can allow it to grow. Attempts to wet clean dry processing environments have been shown to spread contamination and increase the risk of product contamination because of growth in environmental niches like cracks and crevices that cannot be reached by sanitizers. Most strains of E. coli bacteria are harmless, but some strains produce a toxin, Pcqi toxin, that can cause serious illness, including bloody diarrhea, blood clotting problems, kidney failure, and death from consumption of low numbers of cells. Some people get the less serious form of the infection, which can range from no symptoms to diarrhea that starts out watery, then turns bloody. But the infection sometimes progresses into a life-threatening form of the illness that causes kidney failure and other problems, with children and people with weak immune systems being at especially high risk. E. coli 157H7 has caused outbreaks of foodborne illness and is primarily found in the intestinal tracts of ruminants. The outbreaks have been traced to many kinds of foods. For example, undercooked ground meats, unpasteurized, raw milk, unpasteurized fruit juice, lettuce, spinach, sprouts, and more recently commercially manufactured frozen cookie dough that had been contaminated with E. coli 0.157H7 from wheat flour. Contributing factors include produce that has been contaminated by unsanitary irrigation water and contaminated meats that are not cooked appropriately. Listeria monocytogenes is one of the leading causes of death due to foodborne illness. For those with normal functioning immune systems, the symptoms resulting from infection are limited to nausea and diarrhea, which may last for a few days. However, Listeria monocytogenes poses the greatest risk to those in high-risk categories where there are issues with the immune system. For example, the elderly, where the immune system begins to fail, the very young who do not have a fully functional immune system, women who are pregnant where there is a certain level of immunosuppression, and those who have immune diseases or are taking immunosuppressing medications. In these persons, the pathogen can enter and infect the bloodstream, septicemia, and impact the nervous system, meningitis. Listeria monocytogenes originates in agricultural environments, especially farms with animals such as cows and sheep. However, many strains of bacteria involved in foodborne illness outbreaks are strains that have adapted to and become persistent in food processing facilities. The types of foods typically involved are those that are ready to eat, refrigerated, and capable of supporting growth. Examples include raw or under-pasteurized milk, cold smoked fish and other seafood, meats including deli meats and hot dogs, cheeses, especially soft cheeses, and fresh vegetables. Listeria monocytogenes can become a serious contamination concern within a processing facility once it becomes established in the facility environment and equipment. Listeria is hardy, it tolerates salty environments, and can grow at refrigeration temperatures, unlike many other foodborne bacteria. It forms biofilms, which allows it to attach to processing equipment in areas such as within flume systems, and can find harborage in niche environments, such as cracks in equipment and crevices in floors and walls. Staphylococcus aureus, often called staph for short, causes a foodborne intoxication when it grows to high numbers in temperature-abused food. In these foods, Staphylococcus aureus produces a heat-stable toxin, enterotoxins, as it grows to high levels. These enterotoxins are typically not destroyed by cooking, although the bacterium itself can be destroyed by heat. These toxins can cause nausea, stomach cramps, vomiting, and diarrhea. In more severe cases, the toxins may cause loss of body fluid, dehydration, headache, muscle cramps, and temporary changes in blood pressure and heart rate. The illness usually is intense, but normally lasts from just a few hours to a day. The toxins are fast-acting. They cause symptoms within 1 to 7 hours after contaminated food is eaten. The organism is commonly found on the skin and within the nasal passages of humans, and becomes a contaminant in food during improper handling by people. Outbreaks often have been linked to foods that were improperly handled during processing and then were temperature abused by not using proper refrigeration. Examples of foods that have been linked to staph poisoning include meat and meat products, poultry and egg products, salads such as egg, tuna, chicken, potato, and macaroni, bakery products such as cream-filled pastries, cream pies, and chocolate eclairs, sandwich fillings, milk and dairy products, and batters. Factors that can contribute to outbreaks include food handlers, poor personal hygiene, especially inadequate hand washing, and poor temperature control, especially of heat-treated foods in which competitive organisms may have been eliminated. Clostridium botulinum is an anaerobic, spore-forming rod that can cause intoxication. Botulism is the illness that can be the result and is a serious, sometimes fatal, disease caused by a potent neurotoxin formed during growth of Clostridium botulinum. The infection results in flaccid paralysis of muscles, including those of the respiratory tract. Commonly found in soil and water, the spores are heat resistant and can survive in foods that are incorrectly or minimally processed. Any food conducive to outgrowth of the spores and subsequent toxin production can be associated with botulism. Outbreaks have involved canned foods, garlic and oil, and temperature-abused foods, cooked potatoes, stews. A hazardous situation can occur when food processing allows spore survival and growth and eventual toxin formation. Often this is associated with improperly processed canned foods, but almost any type of food that is anaerobic and not very acidic, pH above 4.6, and temperature abused can also support growth and toxin production by Clostridium botulinum. Examples of outbreaks have included garlic and oil mixtures, cooked potatoes, etc. Viruses transmitted by foods cause infections often with low numbers of viral particles consumed from a food that is contaminated. The viruses will not grow in the food, but their presence will cause illness. The virus may also come directly from an infected person, who in turn contaminates food or food contact surfaces that have been contaminated with infectious viral particles, where they may remain infectious for extended time frames. They can also survive in a frozen state. The most common foodborne viral hazards are norovirus, the leading cause of foodborne illness in the United States, and hepatitis A virus. Other viruses, such as rotavirus, may occasionally be associated with foodborne illness, and more may be identified in the future. While the vast majority of viral outbreaks occur in food service settings, outbreaks have been associated with processed foods as well. For example, a large norovirus outbreak occurred in Germany that was associated with frozen strawberries imported from China. Viruses can infect consumers through contact with infected people or contaminated food or water. People who are ill from a viral illness can shed viruses in very high numbers in vomit or feces. Even when they recover from the illness and no longer show outward signs of illness, people can still shed the virus in saliva and feces. Transmission of viruses to foods is usually related to poor employee hygienic practices, such as improper hand washing or working while actively shedding viruses. Therefore, prohibiting people with viral illnesses from coming into direct contact with food reduces the chance for foodborne transmission of viruses. Person-to-person transmission is very common for viruses associated with foodborne illness outbreaks. This is another reason for requiring ill individuals to stay home from work. It prevents other workers from contracting the disease and spreading it to food. Outbreaks have been traced to foods, especially crops exposed to inappropriately treated water. This may be rare in developed countries, but may be a concern in certain regions of the world. Thorough cooking is also an effective control mechanism, and most foods associated with viral foodborne outbreaks are ready to eat. There is some evidence that high-pressure processing may also be effective in reducing the risk of transmitting foodborne viruses, and exploration of validated processes for specific foods is necessary for this control strategy. Norovirus is resistant to typical sanitizer concentrations used for food contact surfaces. An EPA-registered disinfectant with claims against norovirus should be used. A general list of these products is available through EPA, and the term norovirus or Norwalk virus will appear on an EPA-registered disinfectant label. Carefully follow manufacturer's label instructions for use. For example, if used on a food contact surface, the sanitizer may need to be rinsed from the surface after treating and follow with a sanitizer at the appropriate concentration before using the equipment. Like viruses, foodborne parasites do not grow in food. Major foodborne parasites in the United States include Cryptosporidium parvum, Cyclospora cayetanensis, Giardia intestinalis, Lamblia, Toxoplasma gondii, and Trichinella spp. Cryptosporidium parvum is a rarely reported parasite, but is notable for its resistance to chemical agents, including standard levels of chlorine. It is sensitive to drying and ultraviolet light. Cryptosporidium causes diarrhea, and infection can be fatal for immunocompromised people. Foodborne outbreaks have involved apple cider and unpasteurized milk, as well as contaminated water. Cyclospora cayetanensis is a parasite that has seen more reported outbreaks in recent times. It causes prolonged diarrhea. Death rarely occurs. Outbreaks are frequently associated with fruits, berries, leafy green and other salads, and herbs like basil. Giardia intestinalis, or Lamblia, like other parasites, causes diarrhea and is the most common parasitic cause of diarrhea in the United States. Contaminated water is the primary source for outbreaks, but food and people spread the disease, and only one cyst may be enough to cause illness. Illness occurs about 2 weeks after eating contaminated food, so tracing the source of illness can be very difficult. Foodborne outbreaks with identified vehicles include ice, lettuce-based salads, chicken salad, and unspecified vegetables. Toxoplasma gondii is a parasite and a leading cause of death from foodborne illness in the United States, particularly for babies infected in the womb and people with suppressed immune systems. People infected with toxoplasma may be asymptomatic, but it can spread to a variety of organs, including the brain, eyes, heart, and other muscles. Raw meat products and cat feces are the primary source of this parasite. Freezing food to less than or equal to 9 degrees Fahrenheit minus 13 degrees Celsius for 24 hours or more usually prevents infectivity. Cooking meats to recommended temperatures is also an effective control measure. Trichinella species is the parasite that causes trichinosis, which is associated with consumption of raw meat products. In the past, pork was the primary type of meat involved. However, transmission through commercially raised pork is now rare. Trichinellosis is more commonly associated with game meat. As with other parasites, Trichinella is susceptible to freezing and cooking. While foodborne parasite outbreaks are reported less frequently in the United States than viral or bacterial agents, it is important to recognize potential issues and sources and control for these agents. Parasitic foodborne and water-associated diseases are more common in countries with poor sanitation. Consumer exposure to parasites depends on food selection, cultural habits, and preparation methods. Some parasites may be transmitted through food or water that is contaminated by fecal material shed by infected hosts or by consuming infected animal tissue. Methods of preventing transmission of parasites to foods by fecal contamination include good personal hygiene practices by food handlers, elimination of insufficiently treated animal waste to fertilize crops, and proper water and sewage treatment. In specific instances, freezing can be used to destroy parasites in food. Freeze-thaw cycles can prevent infectivity of Giardia, Cryptosporidium, Cyclospora, Trichinella spp, and seafood-related parasites, which are not covered in this training. Parasitic infections are normally associated with raw or undercooked foods because cooking procedures that destroy pathogenic vegetative bacteria also kill foodborne parasites. As previously discussed, biological contamination of food products typically comes from one of 3 different sources. 1. Ingredients. 2. The processing environment, including facility environment and processing equipment. Or 3. People. Controls are needed to manage the hazards introduced from these sources. For example, sometimes ingredient-related hazards can be reduced to a safe level by using process controls, such as a cooking procedure, or maintained at a safe level using temperature control. However, not all products receive a cooking step or temperature control, and cooking may not be effective against some pathogens. In many cases, the preventive control for the hazard is done by the supplier. In these cases, if an ingredient has a history of being a potential source of a particular biological hazard, a supply chain program may be required. This is determined through hazard analysis. See Chapter 6 and 7, Hazard Analysis and Preventive Controls Determination. The processing environment, which includes the facility environment and processing equipment, is a potential source of environmental pathogens and cross-contamination. Cross-contamination occurs when pathogens are transferred from raw products to processed or ready-to-eat products. Direct contamination can occur when raw product comes in direct contact with ready-to-eat foods. Indirect cross-contamination occurs when a food contact surface is used for both a raw product and ready-to-eat product, such as putting cooked product back into the raw product container. Cutting boards, work tables, tools, and utensils, particularly those with hard-to-clean surfaces, are other common sources of cross-contamination. Cooking a product in package can prevent recontamination, but cooking in package is not possible for many products. Effective sanitation controls, including cleaning, sanitizing, and zoning, are useful to reduce the likelihood of post-process cross-contamination. An environmental monitoring program must be used to verify the effectiveness of the sanitation preventive controls. These types of controls are discussed in Chapter 12. Sanitation preventive controls. People with an illness or infection may potentially contaminate the product. Transmission of pathogens by ill employees can typically be controlled when addressed by GMPS and training, which is discussed in Chapter 2. Good manufacturing practices and other prerequisite programs. People can also serve as a vector for transmission of pathogens from a raw product to a ready-to-eat product. Effective hand washing procedures are needed to prevent such transfer. In summary, biological hazards can present a food safety risk if not controlled. The severity of the risk depends on a number of factors, including the consequence of exposure and frequency that the hazard is observed with or without controls in place. Preventive controls must be designed, documented, and implemented for all biological hazards, requiring a preventive control as determined by the hazard analysis process. Because there are many potential hazards that could be considered in the production of food, it is important to identify those that are of such importance that they must be managed using a preventive approach. This will enable the food safety team to focus resources on the most important hazards. The hazard analysis process is an important step to identify those hazards requiring a preventive control. This is addressed in Chapters 6 and 7, Hazard Analysis and Preventive Control Determination. Remember the three main strategies to control biological hazards. 1. Prevent contamination. 2. Reduce or eliminate them. And 3. Control growth. Strategies to prevent contamination must address ingredients, people, and the environment as relevant to the product being produced. When reducing or eliminating pathogens are considered, remember that spores are harder to kill than vegetative bacteria, frequently requiring heating under pressure to achieve effective temperatures. Finally, preventing growth may be necessary, and examples include time, temperature, pH, water activity, AW, atmosphere, competition, preservatives, or combination of these. You have completed the lecture for Chapter 3. Be sure to complete the knowledge check as well as these Chapter 3. Exercise. See you in Chapter 4.